Welcome back, everyone. Let's just jump right into it. Today, we're taking on what might literally be the most audacious infrastructure project of the 21st century. We're talking about space-based data centers. We're going to put on our investor hats for this explainer and evaluate the ultimate balance sheet, weighing the insane potential upside against some truly massive financial risks of orbital computing.
Okay, let's dive into this. To understand why we're even looking to the stars in the first place, we actually have to look down at the ground. Right now, running a data center is staggeringly complicated and incredibly expensive. They demand vast amounts of water, enormous sums of electricity, and just huge tracts of land. So computer architects and tech giants are asking this really radical question. What if we completely bypass these earthly constraints? What if we built our massive computing hubs in space?
And look, this isn't just science fiction. The sheer scale of the ambition here is frankly staggering. Companies like Blue Origin and SpaceX are actively working on this right now. To put it in perspective, SpaceX actually recently filed an application asking the FCC to launch a cluster of up to 1 million satellites specifically to build an orbital data center, 1 million. But, from an investor's perspective, this introduces some pretty massive regulatory risks, especially as the FCC tightens the rules on orbital debris and deployment timelines. So we really have to ask, just how feasible is this financially?
Well, to figure out if the math actually works, we first need to understand the terrestrial bottleneck. Why are companies so desperate to get off the planet? The truth is, expanding traditional data centers means fighting for increasingly scarce, super expensive tracts of land, not to mention navigating incredibly complex local zoning laws. Basically, scalability is severely bottlenecked down here on Earth.
Let's break down the terrestrial baseline. Down here, data centers are absolute resource hogs. First off, they need an immense amount of electricity pulled straight from our already strained power grids. Second, all those working server racks generate intense heat, right? So they require massive evaporative cooling systems. This usually means routing vast amounts of warm water through giant cooling towers so it can evaporate and bring the temps down. And third, to harness all that compute power, these racks have to be physically connected by countless fiber optic cables. It's a lot.
Now shift your perspective upward. Think about the orbital upside here, limitless scalability. If we can successfully relocate these computing hubs into orbit, the potential return on investment is absolutely massive. You're completely free from the expansion bottlenecks of terrestrial infrastructure. We're talking zero land costs, and you bypass the constraints of the terrestrial power grid entirely. But how exactly do you power a massive data center in a vacuum? And this brilliantly illustrates the elegant solution to our electricity problem. If you design these satellites with large solar arrays, you can position them in what's known as a sun-synchronous orbit. Specifically, computer architects are looking at the late-and-dusk line. Basically, this is the exact orbital path where daytime constantly meets nighttime. By riding that line, the satellite gets nearly constant, uninterrupted exposure to the sun, which means access to inexpensive, essentially infinite, free solar energy to power your servers. Now, free energy sounds fantastic on an investor's balance sheet. But let's sober up the tone for a second, because we have to talk about the brutal overhead of space physics. The environment of a zero-atmosphere vacuum threatens this entire investment and introduces some really extreme engineering challenges. The most immediate problem is heat. On Earth, cooling is, relatively easy. We have air we can blow over the chips, so we pipe in extra water for that evaporative cooling we talked about. But in space, there's no air. There's no extra water to pipe in. So instead, satellites have to rely on heavy, closed-loop radiator panels. These systems basically run a fixed amount of water over the hot chips, carry it out to panels on the outside of the satellite, and cool it down by bleeding the heat away via infrared radiation before cycling it back again.
And here is the core financial motif you really need to keep in mind for space infrastructure. In space, weight equals cost. Those closed-loop radiator panels, they're heavy, and every extra pound of weight on a satellite requires significantly more fuel to launch it out of Earth's gravity well. This physical reality drastically drives up the initial capital expenditures, the CapEx, for the whole project.
But heat isn't the only enemy up there. We also have to account for the radiation threat. Space is just full of high-energy particles zooming around. And if just one of these particles strikes a GPU while it's processing data, it can physically flip a 0 to a 1 in the computer's memory. That single bit flip could mean the difference between your server calculating the correct answer to a complex problem or spitting out complete garbage. And over time, this constant bombardment severely impacts hardware longevity. It drives up the overall failure rates way faster than on Earth.
So if our orbital data center is actually going to be commercially useful and reliable, we need solutions. Computer architects basically have three main strategies to mitigate space radiation. Step one is software-based, essentially writing smart code to detect when these errors happen and correct them on the fly. Step two is redundant computation, running the exact same task multiple times on different chips and comparing the results to make sure they match. And step three is physical shielding, enclosing the servers in heavy materials to just block the particles from hitting the chips in the first place.
So the crucial point is the number 3. Because of that second strategy, redundant computation, you would essentially need 3 GPUs in space to confidently do the reliable work of just 1 GPU on Earth. When you factor in the cost of buying 3 top-tier processors, plus the physical shielding, plus the extra weight of the radiators, plus the rocket fuel to launch all of it, man, the hardware costs multiply incredibly fast.
Okay, but let's assume for a second we've paid for the hardware, we launched it, and it's happily powered by the sun. We now face a massive logistical hurdle, the bandwidth bottleneck. How exactly do we get vast amounts of data from our computers down here on Earth up to those satellites and then back down again?
Well, it turns out communication up there is kind of a tale of two technologies. When these satellites talk to each other in their orbital cluster, they can use lasers. By precisely positioning the satellites and modulating a laser signal, they can transfer data between each other at incredibly high speeds. It's amazing. But when communicating from Earth up to the satellite, we have to rely on traditional radio frequencies, and radio bandwidth is much slower.
In fact, the radio bottleneck is so severe that experts point out a really surprising fact. If you wanted to send a massive database from Earth into space, it would probably be faster to load all that data onto a physical computer disk, put that disk on a rocket, and literally launch it into orbit, rather than trying to transmit the whole thing over a radio frequency. Crazy, right?
Obviously, launching physical hard drives every time you want to update your data isn't exactly a scalable business model. But engineers actually have a clever implementation strategy that bypasses this bandwidth bottleneck entirely: the AI preloading workaround.
Here's how it works to mitigate that crippling latency. Instead of trying to send massive amounts of data back and forth all day, you build a massive AI model and preload its entire training dataset onto the server before you launch it. You're essentially sending a fully trained, preloaded brain into space. Once it's in orbit, you don't need high bandwidth anymore. As a user on Earth, you just send up a short, maybe 120-character query. The satellite processes it and only has to beam back a few small text tokens via radio. This approach makes orbital AI inference completely feasible.
So, let's bring it all together for the bottom line. As focused learners and forward-thinking investors, we really have to evaluate if the math actually pencils out for these tech giants.
Think like a venture capitalist for a second and look at the balance sheet. On the CapEx side, your upfront capital expenditures, the costs are astronomical. You have to pay for heavy closed-loop radiators, triple the amount of GPUs for redundancy, heavy physical shielding, and all that rocket fuel to get it there. But you have to weigh those immense upfront launch and hardware replacement expenses against the operational savings. We're talking zero land costs, zero water utility bills, and a completely free, limitless supply of solar energy over the entire lifespan of the satellite.
I want to leave you with this quote from the computer architect we sourced for this explainer. He notes, "The costs of doing this are large and, at the moment, unknown. We need to explore the design space and figure out what combination of technologies will allow us to get to orbital computing." So what do you think? Is putting 1 million servers in space a visionary leap that's going to finally free Earth from the terrestrial bottleneck? Or is it just an astronomically expensive gamble that defies the brutal physics of space? It's a fascinating design space to watch. Thanks for joining me on this deep dive, and I'll catch you on the next explainer.